All right, here's the plan. This is what we're gonna do. We're machine learning. We're gonna walk through and figure out what the very basics are. The introduction. It's actually pretty simple. That's the plan. We want to walk through and see how simple it really is. It was simple. It really is. They do make it seem complicated with fun symbols and a math, and it looks like it's hard. It really isn't. The idea is actually all right. Let's actually walk through it. So, starting with the most basic fundamental machine learning algorithm is a perceptron, supervised learning algorithm designed for binary classifications. That means where the output data is either true or false, and there's nothing else to output. It's either true or false. One of the options for that is when you provide input data, whatever that model is going to see is going to provide output data in one dimension, and it's going to be either true or false. So you can provide a whole bunch of data as the input, but the final output, it's going to be true or false, and that will be the binary classification. This is the great part about machine learning. The idea is that you provide it input data, and it's going to give you answers as the output data. And then the machine learning is in the middle. The cool part, you don't have to write code to build an algorithm to decipher all those inputs and data and then get the output that you're looking for. That's the great part. Machine learning does the middle part for you. So all you have to do is provide the inputs, and the model will give you the outputs. That's the whole point. So just let's walk through this, the inputs and outputs of machine learning. This is the simple part, the introduction part. So we've got the inputs, which is usually called the X, or the features. These are all the same in machine learning. You've got inputs, or the X variable, or the features. That's what the input is. And you can see we've got an array of numbers. And then the output, or the labels, is going to be Y. And that's what the output is. Y is also sometimes called labels. They might call it the ground truth when you're training a model, because this is the actual answers for the data from the inputs. The process of providing the inputs and the outputs of machine learning, this is called the training process. When you have all the inputs and all which are the features, and then the labels, which is the outputs. This is known as training. During training, the perceptron, which is a foundational basic machine learning model, it iterates and adjusts the internal parameters, the weights and biases, to eventually learn and generate the correct output given the input. This is what it looks like. So here are our inputs. If we're going to have a machine learning algorithm learn the AND gate, the AND operator, we say we've got two inputs here, and then here's the output. This is the answer. So what we do is we train the model on these inputs. This is supervised learning. And we put the 0, 1 is going to be 0, and only 1 and 1 is going to be 1. So given these inputs, we should see these outputs. All right, let's walk through the algorithm of a perceptron. This is the machine learning model that is as simple as you can get. You can probably find a simpler approach. That this is, I would say, probably nearly as simple as you can get. Let's look through the perceptron from a machine learning perspective. You have two inputs and a single output, and it looks like this. Actually, let's take a look. There's a whole bunch of symbols here. It looks kind of complex, though it really isn't. It's actually pretty simple. Really, so we have the machine learning weights, and we have a bias. Y is the output, X is the input. So right here at this section, we see two weights, and we see the two inputs and a bias. The weights are going to be floating point numbers below 0, usually like 0.5, for example. So you'd see weight 1, weight 2, these are going to be 0.5. And then you multiply with the inputs, and you add a bias, and you get your output. Really pretty. It seems so simple. Actually, it is a very simple algorithm. You've got your weights, and then your bias, and then you've got your inputs, which look like this, right? So you've got your inputs, which can be 0, 0, and then your output is going to be 0 in that case, or 1 and 1 as the inputs, and then you've got 1 as the output. So if you see here, Y would be the 1, whereas the output, and then X is going to be 1 and 1. Weights are going to be a float, so it could be 0.5. Each of these will be 0.5, for example, and a bias would be the same, 0.5. And during the training process, what we want to do is adjust these weights iteratively, the biases and the weights, to increment them by up or down, so that way when we multiply them and add the bias, it gets our ultimate output of the value that we're looking for, right? So you've got 1, and then you've got 1 and 1, and so that should be the value. So we're iteratively training the model in a supervised fashion to learn the AND gate. and it looks, and given this input data with 0, 0, 0, 1, 1, 0, and 1 and 1, we should only see a 1 as the output when we input the data in the perceptron as a 1 and 1. So just walking through some of the variable names here, x, this is the input data, right? So input vector, which just means an array. It's just a set of numbers. In this case, it's only has 2 elements. It's an element with 2 elements in an array. And we've got our weight vector, which are just, floating point numbers, right? This will be where the intelligence lies, essentially, in the machine learning or the AI. This is where the intelligence lie. Same with the bias. The bias will just help adjust as needed from a linear fashion. You need to add some sort of adjustment. I don't actually know why specifically the bias helps, but it does. And there's more than one way to include a bias variable. You could include a weight with because you can lower your weights to a point where there can be some vanishing problems. You could have an untrainable weight variable in your array, in your weight vector, that would always be pegged to 1. That's another way to kind of do that. In this case, we're just adding a central coefficient or a single-digit number, right? Or it's a floating point number. The y is going to be the output, where it can be either 1 or 0. That's what that means. The output could be either 1 or 0. This is the output to the function itself. And then f is an activation function. And what we need to do with an activation function is like, when do we know the output variable is going to be considered 1 or 0? Because here's the problem. When you multiply these numbers together and you add a bias, you're going to get a number between 1 and 0, which is it's a fraction. So you need to be able to define what the activation function is going to be. In this case, we'll say if it's above 0.5, then we'll just count that as 1. If it's below 0.5, we'll count that as 0. That is an activation function in this case. So, yeah, that's what it is. Right here, they have this is what that means. Fancy symbols all over the place here, isn't it? Doesn't this, they make that look so tricky. So if it says it's great, if y is greater than 0, we're going to return 1. If y is less than or equal to 0, we'll turn 0. So there are some cases here. I would say we'd say 0.5 on that side, depending on what your weights are doing. And it's possible that your weights can go negative. So in this case, based on the perceptron algorithm, they're just using 0 as the rounding error. The most foundational basic machine learning model is the perceptron, and we'll look at the diagram that represents the perceptron. We see it here on the screen. We're looking at the input layer and output layer. Together combined will give you essentially a perceptron. And there are a lot of symbols on the screen here. They are a little fuzzy. What's going on? So you've got your input data, which will be 1 and 0, right? That'll be your 1 and 0. You've got your weights here, which is going to be the intelligence, where the model will actually learn to understand how to represent the output. And then you've got a sum layer where you're adding together all that data and then adding a bias, and then you're inputting into an activation function, which is just going to be a snap function. Like sort of a round is like math.round essentially. So this is your math.round, which rounds a number above 0.5 will go to 1 and below 0.5 will go to 0. And then you get your answer. And that's what a perceptron is. I love how they make it seem so complex with these very scientific notation math variables. Though, guess what? It really is just simple. It's just super simple. The perceptron has 3 parameters, which is going to be a weight with, which is going to be a vector of 2 elements. It's an array. This is an array with two numbers in it. And you've got a bias, which is a single number. Our goal is to determine these parameters by training the model. So we've got our input data, and then we've got our output data. And we need to train weight 0 and weight 1 and the bias with the right, essentially means we need to adjust those numbers so that way they match perfectly with our desired target output, which looks like this. Our desired output and input. So you get 1 and 1, it's going to be 0. And then 1 and 1, it will be 1. 0 and 0 is 0, right? 0 and 1 is going to be 0. 1 and 0 is 0. 1 and 1 is going to be 1. This is the AND gate. This is what we can train our model on, and we will be using the perceptron to do that. All right, let's walk through your first machine learning algorithm. It's really simple. They actually make it really easy. We're going to use NumPy as a math library that helps us do a little bit of math more easy. Don't worry about matplotlib. That's just for charting a graph. We've got our activation function, which is the rounding function, just rounds up or down depending on what the value of x is. Then we've got our training data, input data labels. Our x is going to be our input data, y will be our output data, what the model needs to learn. Then we want to initialize our weights and biases, which are going to be an array of 1D array with 2 elements and the same with 1 element. Random, just like 0.5, right? These are going to be like uniform just means below 0, above 1, below 0. And then we train the model here, and the learning process begins. This is the most complex part of the perceptron, is the training loop, where we multiply the weights and the inputs to get the output, activate it, and then we train it. And we did it! Now we have our machine learning model, and it can learn what you provide. It doesn't seem like a lot of code for something so advanced and powerful as machine learning technology goes. Now, something I've noticed here is that we're not doing a full matrix multiplication from the input data. We're just multiplying the weights with the input. So this is a perceptron with an input of 2 elements, and then we're using weights in the array like this. So usually in, like, say, an SVM or a deep learning model, you're going to use matrix multiplication. In this case, we're just multiplying a few numbers together and then adding them. So we've got our x input, which at the first position, and we've got our x input at the second position. So like, if we take a quick peek here, this is what our input data is. So the first is going to be 0, 0, and the very end will be 1, 1, right? So in that case, and then we've got our y training data here. So this is what our input x data looks like. And then we multiply these with our weights, and then we add the bias, and we're adding together the input, the output of the multiplication. Then we're going to activate it, and then we're going to see what the distance is. Here's the error correction part. This is where the learning happens. Right here, we take our y, which is the output, and it's going to give us some number. We don't know what that number is. Based on what the random initializations were from this uniform step, it's going to give us some number, and it's going to be wrong. That number is going to be wrong. Since we activated it, it's going to be 1 or 0, and we're going to know that it's off by a certain amount. So we know what the truth is, and we know what the model told us it is. And so we're going to find the distance. We're going to see how it's different. And then we're going to multiply a learning rate, and then we're going to adjust the weights accordingly, so that way they know. And I can see that we're applying an x input weight and the first element and the second element of the x input here, which is weird. I don't know why that's happening. Oh, I see. Okay, we need to see what the error is. Okay, so since x is always going to be 0 or 1, this is going to tell us whether we're going to be training this parameter. So essentially, if we are going to train this parameter, this is a sort of a logic operator in this case, where if this is 0, that means we are not going to train this at all. So it's going to be subtracting nothing. There will be no change to this. If this is a 1, then we will be needing to modify based on the distance of how wrong it was, the error correction. So we find what the model told us the answer is, what we know what the answer is, then we subtract them to get the distance and how wrong it is. Then we take we see if we need to actually modify it, and then we define a learning rate, because you don't want to adjust the weights 100% immediately, because then the model really can't learn anything with what you're teaching it. It's just gonna flap around and not get you anywhere. You want to adjust it gradually, and our learning rate is going to be 1%. So with 150 iterations. And this is what that training process looks like. So an epoch is going through all of your data once, and then a sample will be training the model on one element in the training. So a training sample will look like this. So we'll train it on this. So this will be one sample right here at the top, for example. That's one training sample. Here's another training sample. And so we've got a total of 4 training samples, and once we get through all 4, that's 1 epoch. So we're essentially doing 600 training samples in this case, because 150 times 4 would be 600 samples total. So this for loop will go through 600 times, and then that will be enough for the model to learn how to give us the correct answers for the outputs of an AND gate operator. So once we run the training loop of our machine learning perceptron algorithm, what we will see is a series of outputs based on the 600 training samples that we are providing to train the model with. In this case, we're just looping over 4 samples 150 times. This is going to be 600 training samples overall, and this is what the output looks like. So we see here what the we have each epoch where it looks like we're printing once every 10 epochs out of 150 total epochs. The loss is going to be what the total distance of error is, essentially, how wrong the model is. What's really neat is, check this out, only after 40 epochs did the model get 100% accuracy. When the loss is 0, that means it's completely learned your data end to end. Like, essentially, you've got 0 error at this point. Isn't that cool? It's amazing. Only after 40 epochs, and it gets the results and gets them correctly. So we've done it. We've walked through all the foundational logics of a perceptron and machine learning algorithm, the most basic foundational model. Isn't this great? There are some limitations of a perceptron. This is where we need to get bigger into like the neural networks, the deep learning, once you go into that range. So you can use an AND operator, a NAND operator, and an AND operator, but you can't do an XOR gate operator in this case for a perceptron because there is a limitation in the linearity of the decision boundary. So it gets stuck and it can't collapse on any other kinds of results. And so in order to get around that, we can add a hidden layer, and now we are into the neural network phase. This is where deep learning can start coming in, where you will add more layers, or essentially more numbers, more weights, more parameters, and then more series. And we also introduce matrix multiplication, in full matrix multiplication, and that's what the difference between a perceptron and a neural network will be. Just beyond the perceptron is the neural network. This is where we get into real machine learning, where we can leverage the power of a computing algorithm will provide input data and output data, and the model will be able to learn what all the logic gates need to be in the middle in order to give you the exact output. And this is my favorite machine learning algorithm, the support vector machine, and it is a pretty powerful model that has a hidden layer and then inputs and outputs, and it gives you basically what you want, and it works really well. It does a really great job, and so you can do this really easily with scikit-learn just by importing SVM. You have your input data, which is your X, your output data, and then you just instantiate a model and then run.fit, and that's it. You did it. You did machine learning right here. Check this out. Isn't this amazing? You get your input and output data, then you just instantiate the model, and then you run fit. It's amazing. All right, I've got here on my screen in my text editor the example that was provided in the document. We're importing SVM, and then we're also going to import some metrics so we can get an accuracy score. And this is so cool. So this is the data set for training the model. That is, in this case, an XOR operator. The XOR gate and an SVM, since it's a neural network, can learn this information and be able to give you essentially 100% accuracy, which is really great. And I love it because it's got this neat little .fit function, which trains the model. Isn't that cool? So you've got the input data, which is our X, and you've got your output data, which is our Y, and we will train the model to learn based when it sees those inputs. So say if, for example, it sees 0, 0, it knows that the output is going to be 0. If it sees a 1 and 0 or a 0 and a 1, then it knows that the answer is going to be 1 in that case. So this is what the model will learn. So this is machine learning right here, very foundational, and it's pretty fast, and it's powerful, and it can do a lot more than what we're just looking at here. So isn't this cool? So we run fit. There's the results. So all we have to do is give it all the examples. So what you do is you can just provide it the input again, and it's going to tell us what the results are. Isn't this cool? Okay, so let's actually run this model really quick. So let's get into the right directory. All right, then we'll just run the program, and then in no time at all, it learned the whole results. It learned it all. Isn't this great? And it got 100% accuracy because it knows with this kind of data, it's pretty straightforward because you have 100% of all possible answers, and then you have 100% of all possible inputs, or essentially questions that you're asking. So in this case, this is where machine learning, it shines and it can get very good. Where it gets more interesting is when you don't have 100% of all known possible values, and it will give you, you can still, this is where machine learning comes in, you can still use this, the support vector machine, to do the same thing with incomplete data, and then when you show it future values that it's never seen before, it'll have a high accuracy. And that is a machine learning right there, the introduction to machine learning. It's so easy. Look, in just like essentially 10 lines of code, you import a library, scikit-learn, and then you define your data, your training data, you instantiate the model, you train the model, and then you test the model. You did it. You're a machine learning engineer. Isn't that straightforward? It's amazing. It really is that simple.